Welcome back to our tour of the first second in the life of the universe. This is a realm so utterly alien, we really have to try hard to bring it to life, to feel in some sense what it was like. And I suppose the closest one might come is to imagine sitting at the centre of a star, but extend the furnace off in all directions without end. Now, from last lecture, we know that at 1 second the temperature was about 10 billion degrees. This is unimaginably hot. If absolute zero were here and ice here, then steam is here and 10 billion degrees is somewhere over by the moon. Now, as it happens, the density of protons, at least, at 1 second is in fact imaginable. It's about the density of water, 1 gram per cubic centimetre, 1 gram per sugar cube. But remember, in the young universe, light actually outweighs matter by a huge factor. At 1 second, the density of light, actually mainly X-rays, is about 1 ton per cubic centimetre. The radiation alone in this sugar cube weighs a ton. Now, this is the primary quality of those early times, what physicists call the energy density, the amount of energy you find in each cubic centimetre. At 1 second, the E = mc² equivalent is a ton, literally, of energy per cubic centimetre. That's about 5,000 city-destroying hydrogen bombs. This is an incredibly powerful furnace. But the furnace is expanding. Everywhere is moving away from everywhere else. At 1 second, the stuff at arm's length is receding at about a walking pace. And because of the expansion, the temperature and density both drop. Here's our graph from last lecture. We have exponential x-axis with time and scale factor along the bottom and top. A second to a millisecond to a microsecond to a nanosecond. They all have equal steps. And exponential y-axes with temperature and density on the left and right. So as time passes, the universe expands, cools, and thins out, following this dashed line, crossing 1 second here at 10 billion degrees and 1 ton per cubic centimetre. Okay, we're now ready to begin our trip into this graph. We're going to start out on the right and move to the left. We're going backwards in time, so we'll get to more and more exotic conditions as we move through the lecture. So here's a period we're already quite familiar with from lecture 25. About a minute after the Big Bang, when the temperature was a few 100 million degrees, a quarter of the universe's hydrogen was converted into helium. During that brief period, 100 times more hydrogen was burned than in all the stars in all the galaxies ever since. Quite a remarkable few minutes. But that's nothing compared to what we're about to encounter. So let's now go back in time to meet our first major event. It's near 10 seconds when the temperature was 4 billion degrees. This is our first temperature threshold. It's the temperature threshold for electrons. Remember from last lecture, when the temperature is so high that two particles colliding have enough kinetic energy to actually create an electron-anti-electron pair, then all of a sudden the gas becomes filled with these electrons and anti-electrons. So, just before 10 seconds, above 4 billion degrees, the gas has a remarkable composition. This is what you'll find in each cubic centimetre. 1/10 gram of protons, 2 kilograms, that's about 5 pounds, of light, 2 kilograms of electrons, and 2 kilograms of anti-electrons. It's an extraordinary mix, utterly different stuff from anything you've ever encountered. It's an extremely dense gas made mainly of electrons, anti-electrons, and light. Okay, now let's just follow that same transition but going forwards in time. Near 10 seconds and spanning an interval of a few seconds, each cubic centimetre of the universe experienced 2 kilograms of electrons annihilating with 2 kilograms of anti-electrons. Now, before that time, that conversion of matter into energy was immediately balanced by an equal conversion of energy into matter. But as the temperature dropped below the threshold, that backwards conversion of energy to matter could no longer occur. So this became a one-way release of energy. It's a stunningly powerful event, and we just need to let it sink in. For those few seconds, an amount of matter equal to 1,000,000 times all the matter we now see in stars and galaxies underwent annihilation into energy. It makes the hydrogen fusion a minute later look like a damp firecracker. Just think of your own matter annihilating, equivalent to many hydrogen bombs. But back at 10 seconds, we have material 400 times denser than lead everywhere, annihilating within 5 seconds. So what did all this energy release do? Well, surprisingly, the answer is not too much. First of all, certainly, it doesn't produce a rapid explosive expansion. Remember, the universe isn't expanding into empty space, it already fills all of space, so there's nowhere else for it to go. But nor does the energy release make the temperature skyrocket. With so much energy around anyway, the extra input just lifts the temperature slightly, by about 40%. It would add a very slight bump to the dashed line on our graph. But what this event did do was to create all the photons that we ultimately see as the microwave background. So the microwave background isn't just a relic of the 400,000-year-old universe. That's when the photons were finally released, when the universe turned transparent. But the photons themselves are a relic of the 10-second-old universe. Now, this might seem a little bit odd to you. We start with 1,000,000 times the mass in stars and galaxies converted into energy, photons, and we end up today with a microwave background so feeble you have to build a sensitive telescope to even detect it. Where did all that energy go? It's been lost to the gravitational energy. The small, young universe has a very negative gravitational energy. It's tightly bound. But as it expands to become large, its gravitational energy becomes less negative. And that difference is taken from the photons. As they're redshifted by expansion, their energy is drained into the gravitational field. Each of them starts out as an X-ray photon, but ends up 1,000,000,000 times weaker as a microwave photon. Okay, let's continue our journey backwards in time to 1 second, where another fascinating change occurs. And this time it's linked to particles we've not mentioned much before, the neutrinos. Remember that neutrinos are one of the fundamental particles. They have almost no mass, and they only interact via the weak force and gravity, which makes them extremely elusive. They breeze through matter almost as if it weren't there. But back in the early universe, it was so dense that neutrinos did interact. They bounced around in thermal equilibrium just like all the other particles. In fact, you could say the universe was foggy to neutrinos. They couldn't travel far before being scattered. But as the universe expanded and the density dropped, there came a time around 1 second when the density became too low to scatter the neutrinos. And from then on, they just traveled uninterrupted in straight lines. Cosmologists say the neutrinos decouple from the matter because they no longer interact with it. Stated a bit more poetically, the universe turns transparent to neutrinos. The fog lifts. Here it is on our timeline at 1 second. Now, I hope all this is sounding rather familiar to you. It's basically the same kind of situation that made the microwave background. Remember, before 400,000 years, the universe was foggy to photons. And when the fog cleared, the photons travelled without scattering in straight lines, and we now see them as the microwave background. So when the neutrino fog clears, and the neutrinos fly free, they create a cosmic neutrino background. It's analogous to the cosmic microwave background, but instead of originating at 400,000 years, it originates at just 1 second. Now this offers an amazing opportunity for future cosmologists to build a neutrino telescope to observe the cosmic neutrino background and study directly the 1 second old universe. Now I say future cosmologists because, just like the photons from the microwave background, the neutrinos are hugely redshifted, so they arrive with very low energy, and this makes them exceedingly difficult to detect. And I'm sorry to say that making an all-sky image of the cosmic neutrino background almost certainly won't happen in this century, and probably not even in the next. But even without detecting these primordial neutrinos, we still have a pretty good indirect evidence for neutrino decoupling at 1 second, because, as I mentioned in lecture 25, it plays a major role in setting the stage for hydrogen fusion at 3 minutes. What it does is it fixes the neutron-to-proton ratio at about 1/7, and it's that ratio that leads to 25% helium production. So let's see how that comes about. So before 1 second, neutrinos and antineutrinos are busy bouncing around and colliding with particles, and in some cases reacting with them. Here are 2 very important neutrino reactions: converting neutrons into protons and converting protons into neutrons. And when both reactions are in full swing, neutrons and protons are present in roughly equal numbers. But because neutrons are just a bit heavier than protons, that second reaction, converting protons into neutrons, needs energy to make it go. Now this energy can only come from the collision, and so that makes the reaction sensitive to temperature. So as the temperature drops, protons can't reconvert to neutrons, so the neutron population declines. Here's a graph of the neutron-to-proton ratio as time advances and the temperature drops. Notice that both axes are exponential. You can see how the ratio starts near 1, but then really plummets, and by 10 seconds there would be almost no neutrons left at all if it wasn't for the neutrino decoupling at 1 second. This halts all neutrino reactions, so the neutron-to-proton ratio gets frozen at about 1/6, 1 neutron to 6 protons. From then on, the neutrons undergo slow radioactive decay with a half-life of about 10 minutes, and if left alone, they'd ultimately vanish altogether after about an hour. But of course, after about 3 minutes, when the neutron-to-proton ratio has reached about 1/7, the fusion reactions start up, and quickly all those free neutrons get gobbled up by the protons to make helium with 25% abundance. This all works out wonderfully. We calculate 25% helium, we measure 25% helium, and without the neutrino decoupling at 1 second, the whole story would be ruined. Actually, the situation is even better than this. When you do the calculations properly, in order to get neutrino decoupling at 1 second, there must be exactly 3 families of neutrino. 2 or 4 families would give different decoupling times, and that would lead to a different helium abundance. Do you see what's happened here? The observation of 25% helium has effectively measured the number of neutrino families. So going back to our diagram of the standard model particles, we now know there isn't a fourth family yet to be discovered. For reasons nobody knows, nature stops at 3 families. This is a wonderful example of how cosmology can shed light on fundamental physics. Actually, I should bring this subject up to date. This 1970s cosmology result was beautifully confirmed in 1989 when the accelerator at CERN carefully measured the properties of the Z particle. Here you can see the data picks out 3 neutrino families, and it really excludes 2 or 4. Okay, it's time to move on, or in fact I should say back, to our next important event, which spans from 10 to 100 microseconds. Let's bring back the diagram from last lecture that shows how the number of kinds of particle increase as we go to earlier times and higher temperatures, as the temperature thresholds for heavier and heavier particles are crossed. Here's the jump associated with crossing the electron threshold near 10 seconds and a few billion degrees. Well, you can see that between 10 and 100 microseconds, between 1 and 3 trillion degrees, there's a really big jump in the number of particle types as we cross the thresholds for quarks. Now, this jump actually has 2 wonderful events associated with it. So let me go through these now. And this time, I'm going to move forwards in time across this particular transition. So let's start at about 1 microsecond. We have an exceedingly dense gas containing mainly quarks, antiquarks, and gluons. It's 10 trillion degrees, and the density is about 10,000 times that of an atomic nucleus. So these are really packed in there, and they're just freely zooming around, crashing into each other in what is called a quark-gluon plasma. It's a qualitatively new state of matter, and it's wonderfully interesting stuff, and I'll come back to it in a minute. So let's push on to about 10 microseconds, near 3 trillion degrees, or about 200 MeV of energy per particle. This is a critical moment, because below that temperature, the quarks have sufficiently low energy and they are sufficiently far apart that they become bound into tight groups of 2 or 3 to make things like protons and neutrons and their antiparticles. So this transition is called, not surprisingly, quark confinement. The quarks and antiquarks are confined within the protons and neutrons. Now, when you think about it, this is the first of a whole sequence of bound systems that get built up as the universe cools and ages. So below 1 trillion degrees, quarks bind to make protons. Below 1 billion degrees, protons can bind to make atomic nuclei. Below 10,000 degrees, electrons can bind to make atoms. Below 1,000 degrees, atoms can bind to make simple molecules. And at 300 degrees Kelvin, room temperature, atoms can bind to make complex molecules. So we live at the end of a long chain of structures, held within structures, held within structures, each being assembled when the conditions are right, and each step allowing, apparently, greater complexity. That chain starts back in the infant universe when the quarks are bound into protons. Another way of looking at this is that quark confinement is really the birth time for the matter in you and me. Just focus in your mind's eye on a single atom of carbon in one of the cells in your pinky. Zoom into its nucleus and identify a single proton. Stick a flag in it so that you don't lose track of it. Now trace its history back in time. You'll find you can follow that same proton back through all kinds of wonderful places and events, right back to 10 microseconds after the Big Bang, but no further. That's when it condensed out of the quark-gluon plasma. That's when that proton, and all the other protons in your body, was born. Now here's yet another way to connect you to the young universe. Look at your hand and try to see it as a highly concentrated form of energy, locked in a small volume. From Einstein's E equals mc², it's a 10 megaton hydrogen bomb locked in a fist. Now try to see that energy unlocked back in its raw form. Now you have a picture of the primordial furnace. As the furnace cooled, some of its energy got locked away as matter, the matter in your hand. In a sense, your hand is a relic, a nugget of locked energy that reminds us of its birth conditions, the furnace of the young universe. Now, there's actually something even more remarkable about the protons and neutrons in your hand. They're all incredibly lucky survivors of an extraordinary period of carnage that happened almost as soon as they were born. You see, immediately after quark confinement, the temperature was already below the proton or neutron temperature threshold. These are heavy particles, remember? So they have a high threshold temperature, near 10 trillion degrees. But after quark confinement, it's only 1 trillion degrees. So particle collisions can't create proton-antiproton pairs or neutron-antineutron pairs. Of course, nothing stops the reverse annihilation reactions, protons annihilating antiprotons and neutrons annihilating antineutrons. Both produce lots of energy. The upshot is that from about 10 microseconds to 100 microseconds, there is a brief period of monumental matter-antimatter annihilation. It's basically the same as the period of electron-anti-electron annihilation at 10 seconds later. But in this event, each cubic centimetre has 100 million tons of matter and 100 million tons of antimatter, and they annihilate within 100 microseconds. That is one huge conversion of mass into energy. And you've probably already guessed what effect it had on the universe. Not much. At that time, everywhere was 1 trillion degrees. So this huge input of energy just slowed the cooling down a bit. After annihilation, the universe was a few times hotter than it would have been if the annihilation had never occurred. Let's just put these two events on our graph of time and temperature. Here they are. First, quark confinement, followed by proton and neutron annihilation. Now, at this point, you may be a bit puzzled. Going back to our single proton with its flag in it, the one right now in your pinky, it was born at 10 microseconds. How did it, and all the other protons in your body, manage to survive that stupendous annihilation event? Well, the answer is extremely interesting, but I'm going to have to wait until next lecture because I'm saving that topic for then. Instead, I want to use the remaining time a little differently and go back to the quark-gluon plasma before quark confinement. Because I want to tell you about recent efforts to actually make this amazing stuff here on Earth using these giant accelerators I talked about last lecture. Now, most accelerators just collide single particles, protons or electrons. And although that's ideal for exploring the laws of physics that make up the Standard Model, it's not so good if you want to create a real gas with many particles at high temperature. So instead, some accelerators collide entire atomic nuclei together. Something like a gold or a lead nucleus contains nearly 200 protons and neutrons. So when they collide, there's a real chance of creating a tiny region, it's called a fireball, with so many particles that for a brief instant it behaves like a true gas. Here's one of these accelerators. It's called the Relativistic Heavy Ion Collider, RHIC, in Brookhaven. Here's the beam pipe, which is a part of the 2.5-mile ring around which nuclei of gold or lead are accelerated. They collide head-on in detectors like this, one called STAR, and the thousands of particles made in the collision are tracked and measured. And these allow you to figure out the properties of this tiny fireball that was created by the collision. Here's a movie of what happens when two nuclei collide. Don't worry about their flat appearance. It's an odd relativistic effect called Lorentz contraction. They're actually spherical, and when they collide, the protons and neutrons seem to dissolve into thousands of particles that are created in this tiny fireball. It has a density 100 times greater than a normal atomic nucleus and has a temperature of 2 trillion degrees. So it's similar to the universe when it was a few microseconds old. Perhaps the most remarkable result to have emerged from these experiments is that the quark-gluon plasmas behave like a liquid. So the first phase of the universe may have been more like a liquid than a gas. Quite a remarkable result. Now, I should say that these are still relatively early days in the creation of quark-gluon plasmas. The experiments have only recently got going, and the theory is exceedingly difficult. But progress is being made, and I expect we'll be hearing more and more about this peculiar state of matter out of which the young universe emerged. Well, I have a couple more minutes, so let's review what we've encountered in this lecture. Here's our graph of time versus temperature. And starting near 1 microsecond, it was 10 trillion degrees and almost 1 trillion tons per cubic centimetre. An incredibly dense gas, or even liquid, containing all the particles of the standard model, but dominated by quarks and gluons. This is the famous quark-gluon plasma that's recently been created using the heavy ion accelerators, such as the ones at Brookhaven and CERN. As time passed, expansion cooled and diluted this plasma until around 10 microseconds, the quarks and antiquarks became confined within protons and neutrons and their antiparticles. Almost immediately, these particles and their antiparticles began to annihilate, and by about 100 microseconds, almost all of them had been converted into energy, leaving behind only a very few protons and neutrons, the ones that are now inside you and me. Not much happened for a while, until 1 second, when the universe turned transparent to neutrinos, creating what we may one day witness as the cosmic neutrino background. The neutrinos decoupled just as the neutrons were becoming rare, and in the nick of time, their numbers were frozen with 1 neutron for every 6 protons. Now, at that time, the gas was packed with electrons and anti-electrons, but around 10 seconds, when the temperature dropped below 4 billion degrees, they almost all annihilated, making the photons that ultimately went into becoming the microwave background. As the expansion continued, and before the free neutrons all decayed, there was a burst of nuclear reactions that locked the remaining neutrons inside helium nuclei, yielding the present-day ratio of 25% helium to hydrogen. Now, in one final effort to bring clarity to all these different stages, let's look at the names that cosmologists use to give to the various periods based on their dominant composition. And let's use our graph showing the changing number of particle types. So we start on the left in the quark era, when free quarks, antiquarks and gluons dominate in the quark-gluon plasma. When the quarks get confined, we enter the hadron era, the name used for protons, neutrons and pions and their antiparticles. When almost all of these have annihilated, we're left with just the lightweight particles, and so we enter the lepton era. And when the electrons and anti-electrons annihilate to make photons, we enter the radiation era. That whole first second sees an extraordinary cascade of particles, which launches us into the radiation era, which itself gives way to the matter era, with its stars and galaxies and the universe we know so well. But what about to the left, to even earlier times? Can we go in that direction and know anything with any certainty? The answer is yes and no. And that's exactly where we're heading in the next lecture.